you, Mr. Chairman. Good afternoon, everyone. My name is Riccardo Fincato, and I work together with Professor Totsumi at Osaka University. The topic of my presentation deals with a couple damage viscoplasticity model for metals and extended to cyclic loading conditions. So first of all, I will show briefly some development in the rate-dependent plasticity, and then I will introduce the plasticity theory that we use. It's called subloading surface. First, an implementation for the rate dependency material, and then adding a damage variable for taking into account the material failure in the framework of the continued damage mechanics. And I will show some brief analysis. This is a work in progress. This is the initial part of the implementation of the model. So briefly, we decided to develop the theory that was proposed by Bingham model, the overstress theory for the viscoplasticity. Subsequently, there are several models which extend this to homogeneous material, to general materials, and then a series of models that have been developed in the latest year. So in detail, we choose to implement a model which is based on the subloading surface theory. Just a few points to understand what this is about. So first of all, this theory is an unconventional plasticity theory. That means that basically there is an evolution between the net distinction between a plastic and elastic domain, but plastic deformation can be produced for every stress rate which satisfies the loading criteria. To take into account a few points of the model, first of all, we create a new surface called subloading surface, which is created by means of a similarity transformation from the conventional plastic potential, which is here called normal yield surface. And the ratio between the two surfaces is indicated by R. Why we have to use this kind of model? Because especially for cyclic loading conditions, conventional plasticity cannot take into account the accumulation of plastic deformation for loading, which is in the neighborhood of the plastic potential. So we have to upgrade the model to plastic theory, which abolishes this distinction. And in the first formulation, when the similarity center of the transformation is fixed, we cannot take into account a correct ratcheting for the material because we create open hysteresis loops. So an additional improvement is to consider a mobile similarity center, so that follows the plastic deformation. So in this case, for example, in one of the analyses we carried out in our previous work, you can see that we are able actually to catch the correct ratcheting for the material. Now, from the rate-independent model to the rate-dependent model, we have to take into account the fact that material behave differently according to the loading rate. And we update the model to the subloading over stress model, which basically add one more surface, which in this case is called dynamic loading surface. And this is necessary because in the overstress concept, the stress can go beyond the conventional plastic surface. So we have to think about the possibility of the stress to go beyond the plastic surface. Now, this dynamic loading surface is always passing through the current stress state. But the main point of using this theory compared to the conventional models is, first of all, we are able to produce a smooth plastic deformation for quasi-static loading condition, which is indicated by the red line in the right picture. And also, conventional viscoplastic theories obtain elastic response of the material for an infinite rate of loading, which can be corrected by a new definition of the viscoplastic multiplier depending on one parameter Rn, which is basically like introducing a maximum size for the dynamic loading surface, after which the surface cannot expand anymore, so we can produce again irreversible deformation. Now, unfortunately for viscoplasticity theory, we cannot use incomplete implicit method integration like the cutting plane because there is no potential that can be satisfied. So we chose a fully implicit integration scheme in the form of the closest cutting point plane. And we can have a vector of all the variables, the stress, the similarity ratio, cumulative plastic strain, similarity center, and band stress. We have a vector of all the equation, and we use simply a Newton-Raphson scheme, which basically is based on a first approximation for the first-order derivatives. And we can choose between two different evolution laws of the band stress, classic Frederick-Armstrong, or more complex Shabash's law, which consider linear contribution of nonlinear plastic hardening. And in this work, we upgraded the presentation of the overstress subloading model by by introducing also the equation for the evolution of the similarity center, which was missing. So just a brief computational details. The matrix A in the Newton-Raphson scheme is basically the matrix of the partial derivative of all the equation in the vector B against the unknowns of the vector X, and in our program can be automatically allocate the space for all the derivatives depending on which kind of backstress law we want to use. Now, the last step, from a rate-independent model, we upgrade a rate-independent model fully coupled with the isotropic damage variable. So, as a premises, there are several choices we can do to couple the damage variable together with the viscoplasticity. There was a first approach by Lemaitre, where we consider kind of concept of effective stress, which unfortunately cannot be centered in the elastic domain. Is not centered anymore in the backstress because of considering damage backstress evolution law. So there are several options. We chose the last configuration where all the variables are considered in the fictitious undamaged configuration. So basically, we can retrieve combination between these two configurations, the damaged one and the undamaged configuration. Again, the implementation of the resolution scheme is the same, so we still use a Newton-Raphson scheme for the solution, and there is some errors due to the graphic implementation, but anyway, so we use a pure Lemaitre damage evolution law. So there is a limitation about this law that cannot consider the load angle effect. So in the test that I'm going to show briefly some example in which the load angle is not relevant. So we tested the model under one single cubic element for testing the reliability of the model itself, and we promoted, we used a Chabot kinematic parallelism law for a carbon steel parameter, common one, and two different loading rate, quasi-static condition and impact loading condition, to show the ability of this model compared to the conventional plasticity, viscoplasticity model. So these are the three basic tests. The first one is a creep analysis, where we impose the pressure and then we keep the pressure constant. Creep and relaxation analysis, where we impose the displacement and then we keep the displacement constant. And finally, some cyclic loading condition against two different loading rates. So the first, the pure creep analysis, we can apply three different values for the pressure, and then we can catch the primary and secondary creep. But since we couple the model with a damage variable, we can also observe the tertiary creep, which tends to happen according to theory, only for the higher value of the imposed pressure condition. What about the relaxation analysis? We use two different rates, one impact rate load, where we can see the difference between the classic approach, where they predict pure linear elastic response, and our approach, where thanks to regulating the parameter Rm, we can have some irreversible deformation induced already at this point. In the subsequent step, which is the step number 2, the stress relaxed and they tends to lie on the plastic potential in the end. From the relaxation analysis in quasi-static loading condition, basically we have a pure elastoplastic model, so we don't observe any stress decay during the step number 2, and if we apply another displacement, we basically recover the material behavior without any changes. From a cyclic loading condition, we can see that a pure conventional model can just predict a linear elastic analysis. Instead, if we lower the parameter Rm, we can produce elastoplastic, viscoplastic, deformations. From a quasi-static loading condition, this is basically a conventional elastoplastic model, so we can overlap the solution pretty well with a rate-independent model. And again, we can appreciate the smooth deformation, the development of irreversible deformation for our model compared to the conventional plasticity models, which have a kind of a more neat difference between elastic and plastic domains. Now, real case, we focus on lead-free solder materials, which play an important role in electronic devices. This kind of material was chosen because it exhibits rate dependency. Those tests are being done at room temperature, and at the same time there is a progressive shrink of the stress strain curves that can be explained through a damaging process of the material itself. We refer to some experimental paper and some numerical simulation paper, and we took 3 different loading rates. First, we calibrate the model against the monotonic loading, and then we observe the changes in the cyclic loading condition. So, in monotonic loading, we can see that we took the parameter directly from the reference paper, except the Young's modulus, there was kind of an uncertainty, so we took it from average value from literature. We can see there is a good overlap between the experiments and our curves, and we improved the previous numerical simulation carried out by other author. And we decided to model quite well this loading condition, because this loading condition has been applied in 50 loading cycles, in a fully reverse loading cycles. This is the response, numerical model response. We check the peak envelope for the first 3 cycles. There is a quite good overlap. And also we check the hysteresis loop after the 50th cycle. So there is a good approximation, probably a small overestimation of the kinematic hardening material. But if we plot the stress peak envelope, sorry, this is number of cycles, not nominal strain, we can see there is a kind of a linear decay, and it can be quite well approximated by the Lemaitre law, where it seems that the bar was kind of smooth bar, so there is no load angle effect in this kind of loading condition. In conclusion, this model is a model that can implement viscoplastic damaging behavior for materials. There is the correction both in a quasi-static loading condition due to a more smooth development of plastic deformation, and in impact loading we can also regulate the amount of plastic deformation induced during the loading. Test analysis shows good implementation of the model, and we can catch real behavior for metallic materials. Future improvements are addition of temperature and considering different loading conditions, proportional and unproportional, and also test the model